Thanks very much, Ling. Thanks, Van, for organizing this very nice session in honor of our very good friend, Fred Goodwin. I'm very pleased to be here today. I'll try to cruise through my presentation since we're kind of tight. We took a little more time for the first hour on the last presentations. Before I get to my topic today, which is the importance of the modulus of elasticity in repairs, let me say just a few words to start things with about Fred. For those of you interested in football, pro sports, there were rumors recently that Jimmy G would come to Cleveland, but listen, not so fast. Cleveland already got Fred G, and he's an all-around player. Let me say that. Fred's new life started with the pandemic. From what I've heard, gardening is one of his passion with his wife, I think. And more recently, I learned yesterday that Fred started blowing glass, and apparently he's very good at it. Already did a lot of pieces of his own. But I suspect Fred might, his plan is to combine his new hobbies with his lifetime passion, concrete. And I think he might somehow, at some point, blow up concrete, green blown up concrete structures. I think this is his plan. So let me talk a little bit about, more concrete aspects. I'll say just a few kinder words for my friend at the end. So I was asked to talk about this TN that was just reapproved last year. Last time it was approved, it was in 2010. Getting old. And we just reapproved it last year. So the question in this tech note is, how important is the modulus of elasticity as a property of surface repair materials? So first, let's go back to some basic here. We need to draw a line between two types of, when dealing with this, two types of surface repair, either non-structural or structural repair. So non-structural, either the cover, the protective portion of any element, so the cover basically, or sometimes shallow repair, cosmetic repairs. In contrast to what we call structural or load-carrying repair. So we have two examples of these types of repairs here. On the left-hand side, you have the protective repair. On the right-hand side, the structural type of repair. And actually, whenever deteriorated load-bearing concrete is being replaced, we need to pay attention to the load-carrying capacity as well as the stress distribution. And this is where actually this property of concrete, the modulus of elasticity, becomes very important. So this property, modulus of elasticity, is being determined from the stress rating curve that you've got on the right-hand side here. So when you test the material, as you're saying on the photo, in compression, or it could be done in tension as well, but typically we're working in reinforced concrete. We're interested essentially with compressive properties. So when you're testing concrete in compression up to failure, and you're recording both the stress and the strain, you're able to draw the curve that you see on the right. And from that curve, we're able to draw the slope of the curve in the first portion, which is approximately linear. The material is not linear itself, but in this portion, up to a little less than 50% of the material strength, which is more or less the range within which actually the material is loaded in the structure. you can approximate this relationship by a linear relationship, and the slope of this line, which is typically in the standard, drawn between 50 microstrain and 40% of the ultimate strength. This is how you determine actually the elastic modulus. So typically for repair materials, either concrete, OPC, or proprietary repair materials. So for OPC, the range of this property is between 25 and 35 GPa. And for proprietary material, the range is somewhat larger. It goes between typically 18 and 35 GPAs. Just to give you an idea for those not very used with with the international SI system, 25 GPa, roughly it's 3,300 KSI. And 35 GPa is more or less 5,000 KSI. So in a structural repair, one of the requirements, I just said a few words about this, is load sharing. You need, especially when in some more or less important area of the structure, concrete is damaged and you need to replace it to have it being reloaded again. You have to pay attention to this. And so if you have a repair just like this, depending on the respective elastic moduli of the two materials, the repair material and existing concrete, the repair will either draw more or less load depending on these respective values. So if you have a repair material that has a lower elastic modulus, it will be less loaded. And on the contrary, if it has a higher elastic modulus, it will get a larger share of the load, it will get more stressed in this area. In addition to the gravity loads, which actually will solicit the elements, you need also to take into account the deformations that the repair material will undergo, shrinkage, and eventually also thermal induced deformation and eventually stresses, which add to actually the stress that are induced at the interface between the repair material and the existing concrete that are induced by the gravity loads. So these stresses add to the gravity load stresses. So whenever there's a significant difference in the elastic moduli of the two materials, repair material and the base concrete, so you'll have some stress concentration, either outside the repair or in the repair itself. And it causes some very significant stresses at the interface, which eventually might initiate cracking and to some extent, eventually debonding. So let just me show you the result of an experiment. We did many experiments on columns like the one you see on the picture here, 200 by 200 millimeter square section, 1 meter long columns, and they were repaired at mid-height with repair on both sides in order to have a symmetric behavior. And we would test, notably in this experimental program, repair materials with different elastic moduli from very low to very high to see how it would affect the behavior. I just want to show you here, these are the results on the graph. I'll go directly to, if I can. Normally I have, if you see the video on the right-hand side, you'll see the column is being loaded right now. And you see at some point, the repairs on both sides completely debonded from the main core of the column. And if you look at the graph on the left-hand side, the red and pink curves correspond to the deformation as the load was increased, the deformation in the base concrete, whereas the blue curves correspond to the deformations in the repair material, which in this case had a elastic modulus significantly higher than the existing concrete. So you see it deformed significantly less, and at some point it completely debonded. So in this case, it was 5,000 KSI elastic modulus repair material versus 3,300 KSI elastic modulus concrete. So much stiffer, the repair. And this is the only combination where we got that behavior. So we tested from all throughout the range I showed before, 18 to 35 GPa elastic modulus. And the only case where we got this, and repeatedly, was in those situations where the elastic modulus of the repair material was higher than that of the base concrete. So this is for structural repair. We'll get to the answer shortly. Let's talk a little bit about protective repair. In that case, what we need to have when repairing is a material which is able to adapt without cracking, which means it needs to undergo the different strains, such as shrinkage, thermal strains, without undergoing stresses that become too high and create significant cracking. So with this, you need to address the notion of, you see in the title, when we address this aspect of repair, this ability to undergo these induce deformation without cracking, we call it dimensional compatibility. And for that, you need to have a material which can extend as much as possible. And this extensibility comes from the elastic strain as well as the creep strain. So in tension, those two components add up, and actually it defines the ability of the material to be strained before cracking. And it's always a balance. The event of cracking is a balance between, if you look at the equation at the bottom of the screen, the shrinkage deformation and the thermal deformation, when they add up, depending on the degree of restraint, they will cause actually stresses. And these stresses actually, in terms of strain, are associated with the elastic deformation as well as the creep deformation. So as soon as you keep this balance, you have a strain capacity which is equal or exceed, the demand from shrinkage and the thermal changes, the material will resist. So in order to have this compatibility, you need to have high extensibility, which means on one side, low shrinkage. So the driver to the stress needs to be low, and the response, in order to have this extensibility, you need low elastic modulus and high creep. And this was reflected in the recommendations that were issued a long time ago in this Reamer experimental project that was run a little more than 20 years ago by the US Corps of Engineers. So in summary, surface repairs must be both mechanically and dimensionally compatible with the existing concrete substrate. To achieve load sharing as required in structural repair, to minimize cracking, and to ensure that the repair in existing structures act monolithically for the expected duration of the repair. And in order to do this, you need to pay attention to the modulus of elasticity. Again. Sorry. So the answer to the question, how important is this modulus of elasticity? For structural repairs, the elastic modulus should be as close as possible to that of the substrate concrete. So you need it to be stiff in order to take loads, but if it's too stiff, you'll get the type of behavior that we've seen before. It can disbond. And in the case of non-structural repair, protective repair, a lower elastic modulus generally will be desirable in order to reduce the stress and reduce the amount of cracking. So just, if you allow me just a second before I finish, Ling and Van, I would like to thank Fred for all these years. I've been collaborating with Fred for more than 20 years now. I think it dates back to 2000, 2001. You've been an inspiring figure to me in all these years, truly our collaboration, inspiring from your knowledge, both scientific but general knowledge, your ethics, your great sense of consensus, which always was, I think, recognized throughout, in all committees where you've been active, and your friendship, your sense of humor, and your taste for beer, which we enjoyed together numerous times. Thank you so much.